We're going to start here with chapter one. There's not a lot in chapter one, but there is. We're going to kind of take a little bit of stuff from chapter one, kind of poke around a little bit. I will say a lot of chapter one can be very helpful for you. There's a lot of math review in there and stuff like that. So again, if you need some help with some math review, there's a lot of parts of chapter one that will be very helpful for you. It also talks a lot in there. There's some sections about using the calculator sort of properly, and we'll talk about obviously as we go through the class. So there's some good information in there. Like I said, we may just kind of bounce around to a few parts of it, and then really we'll pick up with chapter two is really where the heart of it starts. But again, there's some good stuff out of chapter one and stuff you do need to know, and some review stuff that maybe will be helpful for you. So chemistry, obviously, as you know, does sort of influence a lot of areas of life. You know, chemistry and food, chemistry, obviously, crime scene, chemistry and drug discovery, chemistry, obviously, in nursing and labs that you do and tests that you run. So it does really affect a lot of life, parts of life. And chemistry really is the study of composition, its structure, how it undergoes change, how it resists change. Um, and one of the things that we really deal a lot with in chemistry is matter. And it's really the study of matter. And when we talk about matter, how matter changes, how it changes from one form to the next, matter, as we'll talk about, is pretty much anything that occupies space and has mass. So pretty much anything is matter. And a lot of what we deal with chemistry is, changes in a substance when it goes through, for example, a chemical reaction, even changes in a substance when it goes through physical type changes as it moves from, say, solid to liquid to gas. So matter, as said, is basically anything that occupies space and has mass. And there's really three states of matter that we oftentimes come across. There's the solid state of matter. And in the solid state of matter, typically things are packed in pretty tight to one another. So there's pretty well packed in there in the solid state. There's really not a lot of energy associated with the solid state, which is why things just kind of clump together and not really a lot of movement happening. Um, the next state of matter that we often come across is liquid. And in the liquid state of matter, things are still relatively close to one another, but there's actually a little bit more energy involved in the liquid state of matter. They have enough energy for the atoms, for the molecules to really pass by one another, kind of move past each other. That's why when we think about something in the liquid state, it is fluid, right? You could pour it, right, like a liquid and water and stuff like that. And it's because it has a little bit more energy. Things are able to sort of move past each other, but still relatively close to one another. The last state of matter that we deal with typically is the gas state of matter. And in the gas state of matter, everything has completely, basically broken apart from each other. So that's pretty much going to be your really highest energy state. That is things flying around basically with a lot of energy. The only way they could do that is to have a lot of energy to fly around. As we'll talk about in a later chapter, as they're flying around, there's collisions that occur with the walls of a container. That's what we associate pressure with when we talk about gases, is that those molecules are flying around, they're banging around into things. So a lot of what we deal with in chemistry revolves around these three states of matter. So these are three sort of states of matter. And a lot of what we deal with also is how they interconvert with one another. So when we go from solid to liquid, that's the process known as melting, right? You take an ice cube, it starts to melt, right? So that is the process known as melting. You feel bad about your melted water, right? You throw it back in the freezer, and that melted water goes from the liquid stage back to the solid stage in a process known as freezing. If you have water on the stove and you're making some pasta for dinner, right? You put a fire underneath it, your water eventually starts to boil, right? And that liquid water goes to steam in a process known as evaporation or evaporation or vaporization. So as it goes from liquid to gas, that's a vaporization or vaporization. If you have something that's in the gas state, it can go back to the liquid state. That is known as condensation. You could also have a process, as you may be familiar with, where you could go from solid directly to gas, where you skip the whole liquid cleanup. That is what is known as sublimation. Probably an example you're familiar with, maybe, is dry ice, right? Ever used dry ice, seen dry ice? It goes from solid to vapor, gas, no liquid cleanup. Super cold, by the way. Dry ice, by the way, is not water, it's carbon dioxide, yeah? And very, very cold. You could also go from gas back to the solid state. That is what is known as deposition, like you're depositing something on it. You don't see them too much these days, but CDs, DVDs are really shiny. That's how they got them shiny. They did a process of deposition and dropped some metals on the surface of it and makes it really, really shiny. These are what are referred to as changes of state. Now, when we talk about chemistry, we deal a lot with these sort of changes, what's happening with a substance. By the way, if I'm doing melting and freezing, is that happening at the different temperatures or the same temperature? Melting and freezing actually occurs at the same temperature. So that occurs at the same temperature. And by the way, for water, that temperature is 0 degrees Celsius. That's the normal freezing point or melting point. Same thing over here, evaporation and condensation. That occurs at the same temperature as well. That is your normal boiling point for a substance. That's a normal melting point. Boiling point for water, by the way, is 100 degrees Celsius. It's a normal boiling point. So how can they both occur at the same temperature? It is because when we have a change in state, as something goes, for example, solid to liquid or liquid back to solid, at exactly, for example, water, at exactly 0 degrees Celsius, you actually have both phases happening at the same time. You have like ice crystals. You got some solid water and ice, and also at 0 degrees, you got some liquid water happening at the same time. It's not till you get a little bit above 0 degrees that you fully transition to liquid water, not until you're a little below 0 degrees that you fully transition to ice or solid water in that case. Same thing with evaporation and condensation. At 100 degrees Celsius, you have both phases happening. You have liquid water and you have steam, which is gas, happening. That happens, by the way, at the surface of any liquid. You have liquid molecules jumping out of the liquid phase into the gas, and you got slow moving gas molecules dropping back into the liquid. That is why, for example, if you have a little bit of water on the desk or a table, what eventually happens to the water? Eventually evaporates. And that's because you have liquid water jumping out of the liquid state into the gas state, and you have your friend air that pushes those molecules away so they can't come back. So now what you have is just all that water evaporating, getting pushed away. Eventually your little spot of water will evaporate and not be there anymore, right? Also, why if you have water in a beaker or a cup, it takes a long time for it to evaporate, right? At the surface, you have that happening, but underneath, you have a lot of liquid that's not at the surface that's not going to just get blown away. So it takes a lot longer for something like that to evaporate. Any questions on that there? One of the other major things that we look at in chemistry is energy and what happens with energy as we do things. As we talk about these differences in states, as I go from solid to liquid to gas, in terms of energy, would I need to put energy in to do that, or do I need to take energy out to go from solid to liquid to gas? Which way does energy have to go? Energy needs to be put in, right? So if you think about an ice cube, right? If you put some energy in, like heat it up, your ice cube starts to melt, right? You get liquid water. You take that liquid water, put it on the stove, put a fire underneath it. More energy goes in, right? It starts to boil. Liquid water becomes steam and starts to evaporate. So as you go in this direction, energy is absorbed. And in chemistry, when energy is absorbed, that is what is known as an endothermic process. So if somebody says it's an endothermic process, somebody is gaining energy, it is gaining heat. The opposite is true if we went from gas to liquid to solid. So if you have gas molecules and they're flying around a lot very fast, you have to actually release energy to do that. So if you just think about those gas molecules that are flying around, as they lose energy, what happens is they crush into each other and they don't have enough energy to get away. So they kind of clump together and fall into the liquid phase. Then you continue to remove energy. Liquid phase, everybody just locks in. Now they have no energy to move around. They're just going to lock in to the solid stage, right? So in the processes in chemistry where energy is released, that is what is known as a exothermic process. Any questions on that there? By the way, when we talk about heat and energy, heat travels from cold to hot or hot to cold. Energy, heat, it travels from something that is hot to something that is cold. Yeah. So that is always the flow of heat and energy. So if you think about your ice cube, ever wonder why when you take an ice cube out, it just starts to melt without you doing anything to it? Because when you take that ice out, room temperature in the ice cube, energy from the room flows into your ice cube that's sitting on the table. It picks it all up and now it starts to melt and becomes liquid water, right? You don't have to do much to it in that case. Ever wonder why you put water in the freezer and it becomes ice? When you put room temperature water into the freezer, which one is a warmer temperature? The water. All the energy from the water leaves it. Yes? Now all the energy from the water, those water molecules now come together and freeze and become solid ice in that case. Yeah? So that is what's happening. That is what we see and we look a lot about here in chemistry is that flow of energy and what's happening with energy as we do these different changes or even in reactions. Is this reaction releasing a certain amount of energy? This reaction absorbing a certain amount of energy, right? We see that in all aspects of life. Ever have hand warmers where you break something and then all of a sudden your hand gets really warm, right? That is because that reaction is endothermic, right? That reaction, is exothermic that you just did if your hands got warm. It is exothermic. It's going to release all the energy from that reaction to your hands that's holding it, right? Now your hands are warm, right? It picks up all the energy from that. If you want something that's like a cold pack, right? When you put the cold pack on your knee, your temperature of your body is warmer than the cold pack, so all the energy from your knee leaves, right? And now you feel really cold, right? Because you're losing all the energy right there at that spot, right? Any questions on that? Okay. All right, like I said, we're just kind of move around a little bit here. Let's talk a little bit about scientific method. The scientific method is really about a few sort of processes that occur. A lot of times it all starts with an observation. And maybe you observe something or you observe something that occurs, or maybe you're working for somebody that observes something that occurs. And you're kind of interested in sort of why that happens. And one of the things that you try to propose is a hypothesis. And a good hypothesis is a testable sort of explanation of what you're observing. In science or in chemistry, a lot of times you want to have a hypothesis that you can actually test. You could go to the laboratory, run some type of experiment to try to figure out what you're observing and maybe why it's happening. So once you have a sort of a workable hypothesis, you typically do go and do the experiments. And oftentimes when you do the experiments, you end up back up here. You make some observations. Maybe you make some observations of what you expected to happen. Maybe you make some observations of something that you didn't expect to happen. Then you tell the person you work with, and they go, that's kind of cool. Why don't you go do some more work and more experiments? You may refine your hypothesis, do more experiments, and it can be sort of a vicious sort of circle. But eventually, really, one of two things will sort of come out of sort of scientific method. You could either end up with a law or a theory. And there is sort of two types of things, a law or a theory. You could kind of think of a theory as a working explanation based on some experiments that were done. It may not be correct in all aspects. It may be maybe revisited. It may be shown later on that it's not correct in all parts of it. So it's not necessarily set in stone. It's not something that can always occur in that fashion or may be correct in all aspects of it. For example, a guy by the name of Bohr came up with the theory of the hydrogen atom, which explained how hydrogen releases energy as its electrons move from different energy levels. Works really great for hydrogen, but as you move away from hydrogen, anything with more electron, it doesn't really hold up. So works great to explain one thing, but doesn't really explain, everything else. Dalton's atomic theory, he was correct in like 2 or 3 of the 5 areas that he mentioned in his theory. But later on in more science and more experiments, proved that a couple parts of his theory was not really correct. So theories, again, sort of really explain what's going on, may not always be correct 100% of it. They can be sort of revisited, sort of rethought about, and even said like, yeah, this part's good, that part not so good. A law, on the other hand, is something that always happens the same way, no matter what the situation is, kind of like set in stone. For example, we have the law of conservation of energy, which means energy is not created nor destroyed, but moves from one place to the next. You can't transfer it. That means that when somebody releases, for example, we'll just take our hand, for example. We broke that little thing. It did its reaction that released all that energy. That reaction releases all that energy. Your hand absorbs all that energy, right? The energy doesn't get lost anywhere along the way. So your hand absorbs all that energy. Conservation of energy. Conservation of mass when you do a chemical reaction. If you started with 12 carbons and you end the reaction, you will still have 12 carbons. They may be in different things, but because the mass of carbon is like 12 grams, if you started with 12 carbons to begin with and they're 12 grams, you end with 12 carbons in different things, still 12 grams. You still have the same mass of carbon that you started with from beginning to the end of the reaction. So there are laws which, always sort of work out, and there are theories, again, that are, sometimes correct in certain aspects, not so correct in other aspects. Any questions? All right, we're late.